Wednesday, week 5. We are spiraling very closely to the end of week 5, which means that starting next week, we only have 2 weeks to go until we hit spring break. And then that's officially halftime. It also means, and I will be making more of a big deal about it, and we will have more handouts about it. Our first exam, this one really is a mid-term because it's in the middle of the term, will be Monday of week 7, which is right before spring break. It'll be during the lab in the afternoon, so rather than having lab, that week 7, right before spring break, we're going to have a very short exam. Even though we're having it in the lab, it's not a 3-hour SAT where pencils down. It's just going to, I feel it's a lot easier to ask questions that might be picture-oriented or concept-oriented or circuit-oriented. It's a lot easier to draw it, I think, than it is to answer, on a keyboard or try to make a picture using your keyboard. So it'll be a manual exam. It'll be a real exam. I will write it. It's pretty much the same format we've had for several years now, even before we had all this stuff on Canvas. I write it for about an hour long, and so about the same time that we would have it taking in class. However, I have found that a lot of folks, some of them finish it in 40 minutes and say, great, see ya, have a great spring break. We have class on Wednesday and Friday that week too. But you finish up very early, no problem, get your A and go on. Other folks like to just, bring along some food and bring along some drink and make an afternoon of it and just sit down for a little bit and take the exam. So that way there's no rush. As you know, taking the exam in here, we have a class right before us and we have a class right after us. So if we were to try to fit in a 50-minute exam in here, there'd be no time left over for people who wanted to take their time on the exam. But that will happen. You will definitely know what is on the exam and what is not on the exam. So I'll be handing out a study guide here pretty soon to just let you know that we're coming up on it. This past Monday, we specifically went into lab and started working with this little box. This little, appropriately, it's the color black. So we use that word black box metaphorically and not literally. We usually say a black box is something that you can't see inside. It's an unknown system, or at least it's an unknown process inside the box. But you can tell what goes on, input and output and environment, which you can test that. You can't really see what goes on inside of there. For the exception, though, that this literal black box, of course, the manufacturer has said, well, we're going to tell you exactly what goes on inside there. And to some folks who may not know what the shorthand and the hieroglyphics are for resistors and transistors, and there's a diode, there's a capacitor in there, and wires, this might just be as easy as being a black box. Looks like gobbledygook. But this really is the exact electronic schematic of what goes on inside here. It's really, really tiny. I think I mentioned before, I did take a blade one day and pop this guy open to see this inside, and of course that was stupid, because you can't see it. You can't even see the little tiny piece of silicon here that's supposed to be that. It's like microns, a millionth of a millimeter, really, really small. As you guys know, the chips inside your cell phones contain hundreds of millions of these little circuits on this little chip the size of this guy. So it's almost, take this chip, slice it up by a million, and then say, there it is, you can see it. And if you put it under the microscope, you can see it. So this is what is there, and the only way we can sort of get an idea of whether they're lying or not is to actually put it into our system, wire it up, and then give it the appropriate inputs, and then make sure it gives us the appropriate outputs. And working with these chips that we have for the past few years, we find out that that these chips really do that. And we specifically said, there's our box. We talk about this box all the time inside ISBT, but specifically, we're talking about a real box this time around with that dimple over there, and it really does say LM741, and it happens to be a C after it. That's the name of this type of amplifier. And as we saw, there are 1, 2, 3, 4, 5, 6, 7, 8 There are 8 inputs and outputs. I usually put inputs and outputs left and right. As this thing is listed on the board there, they're sort of up and down. Some are inputs, some are outputs, but we know, we've learned this. This is sort of standard inside the lab. Pin 1, 2, 3, 4, 5, 6, 7, 8. They go around the back. This is an 8-pin chip. And each of these 8-pin chips have a name that goes somewhere. Oh, by the way, this guy is NC for no connection. I forget what all these guys are, obviously. Number 1 is an offset. And number 2 is the negative input. 3 is the positive input. 4 is power supply negative. 5, I forget what 5 is. Another offset. 6 is output. And 7 is power supply positive. Okay? Not asking anybody to memorize that. You wouldn't need to memorize that unless you're at a bar somewhere with a bunch of electronics engineers and you were arguing over drinks as far as who was right. It's just trivia, right? It's just, oh, by the way, this is the case. But because we are using it for real in the lab, it sort of makes sense to sort of understand where these things are, at least name them and know what they are. We always have that sheet available to us. We're not going to memorize it. The important things for us to remember is this is a system. It has input and it has output. And the primary inputs of this amplifier are these guys. I'll go ahead and put it in red. Is power supply positive and power supply negative. The reason being, as I mentioned before, what an amplifier does is it takes a whole bunch of power. Okay, I just spelled power wrong. That's what I do. P-O-W-E-R with no extra letters. That's all we need. It has power on input, and then there's an output, and the power can come out, and then depending on how you control the power in and the power out, we use the term a gate with the transistor, folks. That's this guy. Inside here is the gate. And the gate sort of controls how wide or how open this valve is. If the gate is wide open, then all the power in can be all the power out. If the gate is closed, then all the power comes in, but no power comes out. We talk about open and closed systems. And often, when it's working, the gate somewhere in here is somewhere in the middle. It either lets things flow in or lets things flow out. The gate, in this case over here, is these guys. This is the gate. The gate, they call that negative input and positive input. I know I said this was input, but this is the power supply to this guy. And then the output is over here. So this is in, this is in, there's a positive and negative, and then this is out. And its job is to simply turn on and turn off the flow of the power in to the power out. So I apologize again if we can't see this. We have the sink over here. Here's the faucet. The faucet is a source of water. Here's the drain. It literally is called a drain or a sink. This is the sink of water. This is where the water goes when it's done. And this little adjustable valve over here, it's the gate. If I open up a little bit, I get a little bit of water flow. If I open up a lot of it, I get a lot of water flow. If I close it, it stops. But the sink can only flow the maximum amount of water that is attached to it by the pipes. Okay? It's not magic. It doesn't invent water. It just controls the flow of water. That's what an amplifier does. An amplifier simply controls the flow of this power source or this power supply. So we have to plug the power supply in, and then the gate can control how much of it actually gets through, and then the output gives us what we're looking for. It's the gate that does the work. The gate is the one that does the determination of whether things flow or not. So in this case, we say the gate is the part or the part of the system that actually does the work. It's the one that actually controls the flow. It's the important part. I think I used the analogy last Monday of the bouncer or the person at the door. I know you guys didn't hear about the Apple thing. Did you hear about Paul McCartney being turned away?
Wasn't that into the one after party?
Yeah, there was an after party, and Sir Paul McCartney of the Beatles shows up, one of the most famous musicians alive, and they wouldn't let him in because he wasn't famous enough. Okay, so Paul McCartney, Sir Paul McCartney, he's been knighted by the Queen. Sir, he's obviously has a lot of power, but it was the gate person who said, "Nope, not you. You're out. You're gone. Not going to happen." So the gate, the little tiny gate, controls the output. The reason why I'm making a big deal out of this, great, it's a stupid little chip. I probably will never see a real little chip unless I'm an electronics designer for the rest of my life. Who the heck cares? In systems science, we're going to see this pattern over and over and over and over and over again. And those humans who were in charge of letting things flow, or those people who were in charge of holding back the power and then letting the power come back out, sometimes the humans are called gatekeepers. My favorite word is innovators, okay? These are the entrepreneurs, these are the humans that control the flow of insert whatever you want to control here, okay? If you want to control the flow of new ideas, there's lots of new ideas out there, okay? But your job as the gatekeeper, your job as the innovator, is to open and close this gate and allow these new ideas to come out, and then the question is, where do you send them? Well, you hope to send them to customers or send them to your market. So I am specifically drawing this analogy behind an amplifier which opens and closes or adjusts the flow of electrical power is very similar to what we're talking about inside the human world of flowing goods and services and new ideas in the business world. Okay? And the idea is you would get a great education, a great degree, and then eventually a great reputation of being a good gatekeeper that allows the correct products to flow through here and then hit the other side. We had to wire this physical chip up. We had to wire power to pin 7 and pin 4. We had to wire the battery, which is what we were amplifying, to pins 2 and pins 3. We had a resistor in there. We had a feedback resistor. How easy was that to wire everything up? I know you're not doing it now, so how easy was it to wire everything up and make sure everything's ready to roll? Easy. I'm sorry? Annoying? Annoying's a good word. Easy when you were done. Because when you were done, you didn't do it anymore, right? Once you got it. How easy was it to put the wire in the wrong hole?
Oh, that's easy.
That's easy. Okay. How easy is it to grab the wrong resistor and put it on here and smoke the resistor? Not picking on you. It happens, right? That's easy. Okay. So once it's right and once it's working, you look at it and you say, well, that was easy. It's done. But the actual putting it together and making sure you have the wires in the right hole and you have the right resistors and you have the right pieces and you have the right parts. Again, each individual step, no one's breaking a sweat, but it was also easy to get it wrong or not get it right. Okay? That is why when we were talking about things like semiconductors and this op-amp, this integrated circuit, and diodes, I mentioned at the end, here, this goes here, this goes here, this goes here, that's a Nobel Prize. You're like, wait a minute, that's a Nobel Prize? I thought people had to be really smart and geniuses and lots of years and years. That's easy. That's true. The answer typically looks easy once you see it, but being the first person to get the components in the right order in the right magnitude. This is the right size. It's not too big. It's not too small. That takes some ingenuity. It takes some innovation. It takes some research. But once you get it, you want to share it with everybody. Say, hey, guys, here's how this works. Are you guys familiar with the guys called Wilbur and Orville Wright?
Yeah.
Do you guys know those dudes?
Yeah, the Wright brothers.
Do you know what the Wright brothers did?
They flew the
First human airplane, 1903. 2 years earlier, there was a dude who actually was the director of the Smithsonian down in Washington, D.C. And he received a whole bunch of money. His name is Samuel Pierpont Langley. He's named after Langley Air Force Base, and that's the research center. He was also given a whole bunch of money to do what the Wright brothers did about a year later. And it turned out that one of the things he decided to do was he wanted to make a plane that would fly, but he said, for whatever reason, he was down in Washington, D.C., he thought that he would build a houseboat, and then on top of it, he would build a catapult for the plane. And he would catapult the plane off of the houseboat, and then it would fly. Okay, what would really happen is it would catapult the plane off the boat. The catapult was so strong that it just sheared the wings off of the plane. It fell into the Potomac and sank to the bottom of the river. So then you're thinking, how stupid is that? What? Why? So I guess the thought was, if there was a human inside, it's better to land in the water, like a skiing accident, than it would be to get thrown up against a wall. So in retrospect, you're like, what are you thinking? But it turned out, had Samuel P. Langley known that he didn't need to throw the plane that fast. Of course, the idea is, if I throw it really fast, it'll fly. So he made this catapult. It was like getting shot out of a cannon. But the wings, and you wanted to make the wings light because you don't want to make it heavy. The wings were so light, the first thing it would do is snap the wings, and then it would fall into the water. I'm laughing. No one got hurt, okay, but I'm laughing. It's like, that was stupid. But in retrospect, now knowing what we know today, Samuel P. Langley's a popular name now, but it would have been even more popular if his experiments would have worked. But again, he had all the right ingredients. Anybody know how the Navy throws planes off of aircraft carriers to get them on? It's the exact same way. So when he instead of building the first plane, he was actually building the first aircraft carrier. And again, that's pretty cool. That's kick-ass, building the first aircraft carrier in 1899. That's pretty neat. What a great innovator. But he didn't have the powers dialed in properly. There was too much power on the catapult and not enough power, strength in the wings, and all he was doing was just throwing some guy strapped to, a balsa wood airplane into the water. Let's try it again. Let's try it again. Let's try it again. It was a fantastic thing in retrospect. The ideas were correct. The ingredients were fantastic. Sam Langley did not get a Nobel Prize. Well, actually, the Wright brothers didn't get a Nobel Prize either. They didn't get a Nobel Prize for flying, but they're very famous, okay? So even though they had all the right ingredients, putting them together in the right order, at the right level, and adjusting it, that allowed the Wright brothers to do it properly. They, of course, as you guys know, the Wright brothers were born and lived in Dayton, Ohio. But they wanted to find a nice place that was windy all the time, and instead of landing in the water, they wanted to land on sand. So they went to the beach. They went to Kitty Hawk's in North Carolina and said, it's a great place to fly kites, and let's just do it there. So the powers were correct. They had the power. They didn't chuck their plane. They just took their plane off into the wind, just like you would launch a kite. It was a smart idea. They were not PhD engineers. They were just a couple of dudes from Ohio. They loved to fly. They were printers originally, and then they opened up a bicycle shop, and then they said, "Hey, let's do something neat. Let's be the first people to fly. Why the hell not?" So off they did. Off they went. So the reason I'm bringing all this up is this idea of being an innovator. Sometimes what is required is taking all of these great ideas and then matching the power, matching the size. Sometimes just putting the ingredients together does not get you the right solution. You have to go ahead and dial in the appropriate sizes and scales and powers for these things to work. And it happens to be pretty difficult. So one more retrospective question. What if, instead of trying to build the world's first operational amplifier, or instead of building the world's first self-propelled human-powered flight machine, what if you're trying to build a business? And instead of using wires and batteries, how often do wires do what the hell they want to do? Or do they just flow electricity until they melt? Same thing with batteries. How often do batteries just, you build a 1.5 volt battery, and today the battery decided, I think it'd be great if I was a 20 volt battery. Off we go, 20 volts. It doesn't happen, okay? So in working with inventing a new physical device, at least your parts behave and do what you ask of them. As a human who's trying to build a new business and you employ people, what's the possibility of them wanting to do things their own way or not following directions exactly? That happens sometimes. Not saying it's bad, it just happens sometimes. So in studying systems of machines, mechanical systems, systems of pieces and parts and electronics, that, well, it's easy to make a mistake, and gosh, I'm surprised it worked, and it took an extra hour to figure out what was going wrong. Imagine how much more complex it is to start a new business or to start a new industry, and you're working with people. You're working with people on your side, your partners and employees, and then you're working with people who are not on your side, they're customers. Hopefully the customers do what we expect them to do. And then you're working with people who are against you, your competitors. So we have lots of humans that it fouls things up pretty quickly. The fact that one in, I don't know, like Business 100 right now, do they ever throw quotes at you how many businesses survive? Is it 1 in 100 these days? 1 in 10, 1 in 100, 1 in 1,000? Even these really, really awesome, great ideas, it's sort of like figuring out how to do something with wires and batteries in a circuit, but with people you have this extra wrinkle of sometimes they want to do what they want to do, and all of a sudden you thought you were designing something cool, and it didn't work out because they weren't following your design. So with that introduction, in a few minutes, I'm going to start talking about more concepts from our book. I don't want to demoralize anybody, it's just that after figuring out how difficult it is to make something with electronics, and then realizing that making a business is probably 1,000,000 times more difficult, you're like, screw that. I'm not doing that. But that's often, it's not surprising that sometimes really great ideas for businesses just don't work out. But then also, if you go back and look at what happened, another business might come along that has almost the identical idea, and it takes off like gangbusters. You go, wait a minute, how come that worked and mine didn't? There's just so many factors that go into it that it's difficult to figure out what the actual secret ingredient is. Okay. Let me push a button here. So just to show you, we're going to take a look at chapter 2 from our text. Again, getting the text and reading the text is not mandatory. Not required, but if you have it, we're going to be talking about chapter 2. These are concepts that we've been talking about. They're called systems principles. It's inside of Prezi here. Let's see what we got. Turn this on, push this button. Fantastic. All right. The textbook in chapter 1. We were talking about mechanical systems like these electrical things, and mentioned the Wright brothers, bicycle designers. A bicycle is a mechanical system. It happens to have a rider, but the system itself, it does what you tell it. And then one of the things we got to the end, we said, well, wait a minute. What about systems that have people involved? And and those people have brains, and they can go ahead and decide what they want to do. This is the title that this author likes to say. These types of systems, these systems that involve people, and often we call them businesses, which is why our textbook has managing business architecture. They call it a purposeful, multi-minded system. This was that number 6 out of 6. It's a system, first of all. It's multi-minded because now we have people as parts, in addition to individual wires, and everybody is there for a purpose. Everybody's there for a reason. Depending on your society, in some societies, people have to do what you tell them because in your society, you're the strong person and they're the weak person, or you're the king and they're the peasant. It's just how society-wise. That's not how our open democratic society works here in the United States, thank goodness. We still have to worry about these things. So 1, 2, 3, 4, 5. Again, 5 is not a magic number. We're not drawing a pentagram and jumping around. It's just to be 5 topics. So openness. We've talked about systems being open and closed. We know that our operational amplifier is open to the gate. If the gate isn't putting any information in, nothing's happened. It has to be open to its power supply or it's not turned on. In the case of a human system, it's also open. In addition to being open to people coming in and coming out, employees coming in and out, it's also open to new ideas. So it's a living system. It can be understood in the context of their environment rather than just killing it and looking inside the box. We can see how it behaves. Another thing we picked up from this author. It usually involves this huge word, which is really, really big in the business school, really, really big in ISBT, and that's leadership. How do you convince all the parts of your system to behave as, I want to say as they should, behave in the best interest of the system, okay? If we want to win a baseball game, I hope all of the players play their positions to the best of their ability. And this thing down here, guided by an internal code of conduct, the authors like to call it a DNA, sort of like deoxyribonucleic acid. If left alone, open systems tend to reproduce themselves. This is sometimes people blame it on education, but it's cultural as well. If you've learned in college or high school that your team or your organization needs a few people in charge and then a few people who are workers and a few people over here who are in marketing, back and forth, it seems that a lot of these businesses arrange themselves in this way. It's not specifically written down in an instruction manual, it's just sort of how we do things. Purposefulness. Unlike this operational amplifier or the resistors inside this amplifier, the resistor, which is mechanical, will do its job until it can't. And when it can't, it will either break or it will catch on fire. That's how resistors stop doing their jobs. They smoke and they catch on fire. However, thankfully, unless the person is really, really constrained by other choices, someone who has been asked to do something like, oh, by the way, can you hold this leash? What's it attached to? Oh, it's really attached to a very, very hungry tiger. I'm going to go to lunch. And I'm out. I'm not going to do that, okay? Humans are not machines. They're not robots. They'll do things for their own reasons, but they usually have a purpose. Why did you get up and come to work today? Why did you come up and come to this class today? You're having second thoughts like, why the hell did I come up to this class today? There's a purpose, okay? And usually somebody has to convince you that you're doing it for the right reasons, okay? So people who have purpose also have choice. We have to think there's independent choice, independence of choice and free will. And now we're going to talk about an ethics class or a philosophy class. There's the author of our book says that choice has three sort of components. There's the rational choice, which is self-interest. I was hungry, so I went and got lunch. I was hungry. I knew I didn't want to be hungry later on, so it was a very rational choice. There's an emotional choice. Oh, did you hear that Beyonce's over at Starbucks? Oh, okay. I wasn't thirsty, but off I go. Yay. This is the excitement. This is where the marketing department comes in. You can get people to buy your product because they're very excited about it. You get hyped about it. And then there's cultural as the default. It'd be great. Unfortunately, it's kind of chilly up here, but if it was really, really warm in Pennsylvania, I would love to have a siesta around 2 o'clock. That'd be great. Culturally, everybody's just going to sit down and we're going to have a nap. Because a nap afternoon is fantastic. That's sort of a cultural thing. It's not so much rational, it's not so much emotional, it's just what everybody does. We're all going to take a nap at 2 o'clock instead of go to lab. That's fantastic. So this purposefulness is something that we have to concern ourselves with when, as entrepreneurs and innovators and designers, as ISBTers, we have to realize that the parts we're working with are people, and we have to make sure we know what this purpose thing is, rather than just saying, do your job, I expect you here tomorrow, and obviously I just write that person off because they'll do their job. They may not, and if they don't do their job, then the system falls apart. So typically, that requires a whole bunch of other stuff in addition to just instructions to do their job. It also involves information, what questions, what products do customers want, what should we make as our company, how questions, how do customers use our product, and why questions, sort of this idea of information, knowledge, and understanding. And these three things happen to be in an area that has been known, and continues to be known as information and knowledge management, and it's something that we do a lot of here in ISBT. We have biotechnology, we have energy and natural resources as another concentration, and then later on when we ask you to pick concentration in ISBT, information and knowledge management is one of those guys. Businesses are concerned with this because, again, they have to manage the purposefulness of their employees. This is right out of the textbook. Concerning purpose and why. The rational choice is usually safe, is risk adverse. I'm going to do the safe thing. The emotional choice, obviously, is exciting. It involves risk. Hey, I can meet Beyonce. That's kind of cool. Or maybe not. I'll just go past her bodyguards, shake her hand. That'd be great. Or I'll get beat down. But I'll try anyway. It's exciting. There's risk involved. And then the idea of doing cultural is just, again, everybody's doing the same thing. So it's neither of those guys. How things should be done, and the author gets on his soapbox and talks about this. The realities of how things should be done, they remain, and everyone sort of does them that way until somebody challenges them. So this is the idea of being an innovator and coming up with a new way of doing things. Asking the question, why do we always do it this way? Or why do customers always do it this way? Or why do people always buy that product and not a different one? If you're willing to challenge that reality, then perhaps you can change it. A reality does not have to be an absolute truth. It doesn't have to be an absolute reality. People in Philadelphia always eat this particular product, or they eat this restaurant. You can change that by changing the reality situation. Giving your employees and giving your customers a choice implies they're going to make a wise choice. So it implies a power to make the proper choice. You guys aren't parents yet. Maybe shortly. Maybe a couple years. Maybe you have a younger brother or sister or a very young niece or nephew. Giving your toddler or giving a toddler the choice to not go to bed because they're not tired. Is that something that parents usually do? Time for bed. I don't feel like it. Okay, stay up. It's time to eat. Nah, I'm not hungry. That's okay, don't eat. Let's go cross the street. Okay, I'm ready to roll. Nah, we should probably wait for the traffic to stop. Nah, let's just walk. Okay, so when we give humans a choice to make the correct decision, we expect them to have the power to make a competent decision, to make the correct decision. Even though it might be exciting, or it might be risky, or it might be cultural, we expect them to make the most appropriate decision for themselves. But that has to be with some sort of knowledge of what the consequences are. I just grabbed this out of the book. This idea of, here we are in Philadelphia, we have the Liberty Bell down the street a little bit. I never can see it from here if only it was out of the way. There's Liberty Bell, fantastic. Liberty is great, freedom is awesome. However, if you set everybody free, if you set all the kindergartners free at the elementary school, you're not going to get much, other than people running around like crazy people, because they may not have the competence to structure their own little tiny group and feed themselves and clothe themselves and protect themselves. Because giving employees freedom to do whatever they want to do, or giving customers freedom to choose whatever they want among different products, not very useful unless they have some sort of competence. So in the United States, what do we do with young 18, 19, 20, 21, 22 somethings before we set them free into the world and say, go off and be awesome? You guys sort of know. How do we improve their competence at doing things? How do we make sure that they know enough of the risks in order to make informed choices? You don't really know. What mechanisms do we have in place to make sure that late teenagers can make good choices, life choices?
We reward positive behavior and we punish bad behavior.
That's true, especially in younger children. Maybe even in older children too, right? You're going to jail. You're done. What am I getting at? Colleges and universities. We invented this thing called colleges and universities. Why in the world would, as a society, we put so much effort into building colleges and universities, and then ask you guys to pay so much money to go to colleges and universities? As a system, we hope that the college and the university can improve this part. Not that you're incompetent, just that not having yet experienced the world, perhaps learning about the world and learning about real-world situations will give you more competence, so that when you do see something in the future, or you do have a power to choose, you can make a better decision. Which again, it can be a practical decision, it can be an exciting decision, or it can be cultural, but we hope that you have the power to make the correct decision. This gets us back to here. The diodes and the resistors and the wires inside this operation amplifier, we like to think they have no choice. They just do what they're told to do, and they'll do it. They'll keep on doing it until it explodes or shuts down. We don't want mind-numb robots running around. But the thought is, as a society, the reason why we spend so much public money on K through 12 education, and then we, as a society, parents and other folks make sure students have an opportunity to go to college. The idea is, if you have an educated society, then you could build really cool systems, more of them, faster, more often, because you have the folks that know what to do. We're not asking anybody to become a better robot. We're asking you to become a better citizen, part of this system. So you're already part of a bigger system just by being attending school and living here in the United States. Another topic is this idea of multi-dimensionality. What that means is, rather than being a single dimension, you guys have done this before, we've done this before inside physics last semester, there's an axis, we'll call that the x-axis. A dimension is an axis on which you can measure a position. So this is the x dimension. So this is 0, and this is 1 meter, and this is 2 meter, and this is 3 meter. And sometimes in talking about choices and talking about making an informed choice, how do I behave most appropriately? What choice do I make most appropriately? Some folks like to think in a single dimension and say, you're either on this side of the issue, or you're on that side of the issue, or you don't care and you're in the middle. It's a single dimensional thought. You either love vegetables, you either hate vegetables, or you couldn't give half a crap about vegetables. It's a single dimensional issue. When it comes to politics, you're either a right-wing nutcase or you're a left-wing bleeding heart, or you're independent. Okay, who's they? There's a tendency to describe choices as simply a yes, no, or I don't care. For, against, abstain. This idea of being very, very linear. The difficulty is, usually, most often, many, many choices, unlike resistors, human choices are not along a single dimension. They are on multiple dimensions. Here's why. This is where we spent most of our time last semester in physics. We had back and forth x, and we had up and down y at the same time. And if we wanted to spend more time, we would have added z in and out, and made it a multi-dimensional problem. So now, instead of saying you're either on this side a very high value of x, a very low value of x, or you're in the middle, instead of saying it's either or, you can say it's and. You can say one issue is on the x-axis, but the opposite is not negative x, it's on the y, so you can be both at the same time. In this case, we're talking about and getting rid of ors. The choice is not one or the other. It's you can choose both if that's what you want. So how does this actually work? So here's the picture that we're going to end with today. We're talking about innovation and innovative abilities. We're in the School of Arts and Sciences. For those of you who are true freshmen, you heard me give a version of this talk on the first day of school. I think it was Friday. I gave that big talk about Steve Jobs and the arts and the sciences. So you've seen this before. This is what we do in ISBT, obviously. Instead of saying that somebody is a really awesome artist, or they really suck at being an artist because they're a scientist, what we do is say, you can think very artistically and you can think very scientifically at the same time if you look at the problem as an and rather than an or. Just putting the axis here and saying you're either right-brained or left-brained, here's art and here's science, one or the other, choose one. We like to go ahead and say both at the same time. We'll finish this up on Friday. I want to lay this on you. Scientists usually have a great ability to find similarities among objects that seem to be different. And then artists have the complementary ability, the ability to find differences among objects which seem to be similar. So, and there's huge implication as to why these are important. But it turns out that ISBT is all of these guys. If you sort of turn off your skills and you just do what you're supposed to do, you're just a robot. We call those the doers of just what are you doing? Washing dishes. Doesn't require a lot of artists or a lot of science to wash dishes. You know how it works. However, if you're using the art side or the art function, you can find out what the problem is. If you're doing the science side, you can solve the problem you have at hand. And if you do both at the same time, we call those folks innovators. They discover problems and they solve them. We like to think that's where ISBT lives in the club. So I'll use that as our launch. We'll finish up this discussion on Friday. Again, we're trying to transition between this class is all about resistors and wires and pieces to it's actually about people. Because that's what we're talking about.